Hello, everyone. During class today, I had a few different students ask a very similar question about horizontal stretches and compression. And I think generally speaking, every student that brought this idea up kind of understood what should happen, right? What we should do mathematically speaking when we stretch and compress horizontally, but they just weren't quite sure on why they were observing what they were observing, right? That question right at the top of the page is a version of what I've heard from a few of you. Okay, but why does that happen? Very great. It's great to hear as a teacher. Excellent question. So let's take a look. We're going to start with our old standby, old faithful, as our parent function, our quadratic function. And I'm actually going to limit us. We're just going to deal with 0 and our positive values. I think you've dealt with quadratics enough to know, that this is going to work whether we were in the positive or negative direction. So what I'm going to do is just fill in this table, and I'm going to go a little bit further than we normally would. Our input here is x. Our output is f of x. We know that when we square, we're going to get 0, 1, 4, 9, 16, 25, and 36. And we can even plot those points, right? We know 1, 1 is going to be somewhere here, 2, 4, 3, 9, 4, 16, 5, 25, and 6, 36. We'll get that familiar parabolic shape that we all know and love, right? Looking something like this. Right, this is our parent function, right? Our simplest, most boring version, we'll include 0, 0, our simplest, most boring version of a quadratic. And what I think has gone well is when we have a vertical stretch. So I'm going to use a different color here just so we can see the difference. Again, we're going to take x as our input, and we're going to use g of x as our output here. And what you'll notice is there's no parentheses here. There's that 3 is not being squared. It is external to the operation. So this would be a vertical stretch by 3. And what I've found historically is that this makes sense to us because the tables make sense to us, right? If I square 1 and then multiply it, I get 3. If I square 2 and multiply, I get 12, 27. I think these numbers are going to get a little unwieldy soon, right? Squaring 25, we're going to get up to 75. We're off our graph at this point. 6 when we square it is 36. Multiplying that by 3, we're already into the triple digits there. And if we were to sketch this, right, our 0, 0 and 1, 3, what we'll observe is that a graph that gets taller much quicker, right? 448 is off our graph. As I said, I think that observing you all during class these last couple of days, this is something we're pretty comfortable with. We can see that this 3 here leads to a multiplication of our y values, right? It doesn't affect 0, but 1 turns into 3, 4 to 12, 9 to 27, and so forth. I think intuitively, right, in our gut, in our brain, we kind of believe this to be true, and it feels comfortable, right? It makes sense. Vertical stretches, our y values get 3 times as big. What I want to look at is a third example here, and we're going to go a little bit slower through let's get a nice color for this one. We're going to use h of x equals the quantity 1/2 x squared. And so I'm going to write in our labels here, that's going to be x and h of x. And we're going to use those same inputs we've been using, 0 through 6. So 3, 4, 5, and 6. So let's plug in and let's fill out our table, and hopefully this will make a little bit more sense as we leave. So if I were to plug in 0, 0 would be plugged in, for this x here. And again, we're going to double 0 divided by 1/2. Still going to get 0, square it, we're still at 0. Once we plug in 1, we're going to get 1/2 squared, and the result there is going to be 1/4. When we plug in 2 squared, we take 1/2 of that quantity. So what we actually end up squaring is 1 and we get 1 as a result. When we plug in 3, we will have 3 halves quantity squared. That's going to be 9/4. And when we plug in 4, we divide that by 2 to get 2, and square that, we get 4 as a result. When we plug in 5, we'll get 25 over 4. And when we plug in 6, we're going to get 9 as a result. So what I want to do is just look at, you know what, let me pull this other table down here so we can compare it. I'm going to grab our parent function table and just move this down. So just so it's clear, our parent function here is on the bottom. And what we see in pink there is our horizontally stretched function. So what we want to ask as we look at this table is, where do we see similar outputs? So we can see that 0, 0. Oh, that's an eraser, excuse me. Can I undo that? Oh, no. Oh, we're back. Okay, cool. So if I have 0, 0 and 0, 0, not much going on there, no major surprises. But let's pay attention to some inputs. Let's pay attention to those easy to use inputs on h of x. Sorry, excuse me, easy to use outputs on h of x. Here I have 2, 1. At 4, 4, I have a nice easy to work with input and output. And then finally at 6 and 9, I can see that I have nice easy numbers to work with. So let's see what happens when we graph things. So we saw the graph of our parent function. We know 0, 0, let's put that in black. 0, 0, 1, 1 is somewhere right around here, 2, 4, 3, 9, 4, 16, and so forth, right? We know what this graph looks like. That's our quadratic parent function. And then if we look at what we have highlighted here in our transformed graph, right? Those highlighted points, those nice, easy to work with points that I was mentioning, show up at 0, 0, 2, 1, 4, 4, and 6, 9. Right about there. So as I compare this to my original function, the x components are horizontally twice as big as what we would have expected, right? That is why this graph here has a horizontal stretch by 2, right? When we plug those values in, what we end up doing is we actually divide our x values in half. It has the result of requiring a larger input in order to achieve the same output. And as we talked about in class, the reciprocal is also true, right? If I had a different function, let's call it w of x, and it looked like 2, that shouldn't be a fraction, 2x quantity squared, this would represent a horizontal compression by the reciprocal of 2, 1/2. Why is that the case? The same logic applies, right? When we act on the input value, we require a smaller input to achieve the same results. Hopefully that helps make some more sense.